All right, here we go with one of those dadgum informational slides. There's not a lot of math on this slide, but a lot of things that you need to understand as you work through the different ways that instantaneous velocity and derivatives work in real life. Okay, so one of the things that we can get from all of this is what's called displacement, and it's the first term listed here. It's the change in position of an object over an interval of time. Okay, so just how the object changes its position. We don't know how it's going to change it or where it's going to change it to. We just know that it's not going to be in the same place from where it started. Okay, so if the position function is f of t, and position is usually shown with this letter S, so anytime you see that letter S, we're talking about position. Okay. Then the displacement over over some time interval from t to t plus delta t. Now remember, this just represents a stopping point, so this is where I would stop, t plus delta t. This is where I would start. So gosh, all of a sudden all this looks familiar. Is going to be our change in position. So displacement is where the time you stop minus the time you start over the entire travel time. Okay, and that's the function for the time you stop. So when we look at this guy, the function where we stop minus the function where we start all over your change in time. It's exactly what we've been doing all year. It just looks different because the letters are different. The process is the exact same thing. So don't worry the small stuff on that one. You've seen it before a lot of times. Let me just put a parenthesis in here. Instantaneous velocity then is the derivative of position. So if we said that position, if we're talking about position is this S guy right here, this is position, then velocity is the derivative of that. So S prime is going to be my velocity. And oh, by the way, this guy right here looks an awful lot like this guy up here, just no limit. Okay, so we've worked with both of these several times. So anytime we want to know the instantaneous velocity of anything at a specific time, just take the derivative of the position function. When you take the derivative of the position function, you've got that instantaneous speed. Okay, the next one is the speed, and speed is a little bit tricky. It's just absolute value of the velocity function. So once you've taken that derivative, remember your instantaneous velocity could be negative 50 miles an hour. We could go backwards 50 miles an hour. Well, what was our actual speed? 50 miles an hour. Even though we were in reverse, it's like when you drive in your car, the speedometer only shows positive rates of change, positive speeds. And so even when you're backing up, your car would still quite possibly tell you, hey, you're going 20 miles an hour. It wouldn't say negative 25 miles an hour. So when you're doing that, the speed is just absolute value of velocity. All right. Last thing is acceleration. So acceleration is the derivative of the velocity. So if my position function is s, okay, this is position, and if s prime is velocity, then s double prime, which is equal to v prime, will be equal to my acceleration. So when you're asked to find the acceleration of an object, take two derivatives. If they give you a velocity and asked to find the acceleration of an object, take a single derivative. So all of these things are related, and we'll actually talk a little bit about the third derivative, but I don't know if we talk about that third derivative in this particular section. So I think we're good on that stuff for now. So start with position. Apply a derivative, have velocity. Take absolute value of velocity, you have speed. Take derivative of velocity, you have acceleration. Three very important things, and if you're taking physics, those things also come into play quite a bit. Okay? Information slide here. We're going to practice what we've just looked at with the next example.